I would like to introduce our first speaker, who is Shaan Nagy, who will be speaking about automating unrealizability logic, Hoare-style proof synthesis for infinite sets of programs. And I'll hand over to Shaan.
Thanks. Hi, everyone. My name is Thank you. So you can think about this for a minute, and you'll find that, in fact, there is no expression derivable in this grammar that's equivalent to x, or y. Now, one way that we can show that is to consider an input-output example satisfied by x, or y, but not satisfied by any term derivable in our grammar. In particular, for example, if you start with x equal to 1 and y equal to 1 and evaluate the expression x, or y, you'll get the result 2. However, and odd are parity-preserving operations, which means if I take two odd values and I take the and of them, I get an odd value. And similarly, if I OR two odd values, I get an odd value. What this means is that if I start with odd inputs, for example, 1 and 3, and I and OR them as much as I like, I'm never going to be able to get something even like 2. In other words, if I start from a state where x is equal to 1 and y is equal to 3, and I evaluate any expression derivable from the non-terminal e, then the result that I get is not going to be equal to 2. So as far as proving these kinds of properties automatically is concerned, there are a few existing solvers, these top two rows here, Naya, Nope, and Messy. So these solvers are designed specifically for the scenario where you have an infinite set of programs described by a grammar, and you have some collection of finitely many examples, and you want to show that there is no program in your set that satisfies all the examples. Or said another way, every program in your set fails at least one example. So for problems like the one I just showed you, these solvers work great, but there are a lot of kinds of things that they can't do. For example, even when you have a sort of simple functional specification like before, sometimes there doesn't exist a finite set of counterexamples that invalidate all the programs in your set, and so you need actually an infinite set of counterexamples, and we'll see something like that at the end. And similarly, sometimes you're not interested in proving example-based properties. You're interested in establishing the correctness of arbitrary Hoare triples over your set of programs. And this also isn't well supported by this idea of using finitely many examples. There's this Hoare-style logic, this program logic called unrealizability logic that lets us reason over unrealizability triples. And this supports lots of different kinds of specifications, but there is no automation existing for this work. And so it's sort of a purely theoretical construct that is not, for which there exists no automated support. So today I want to talk to you about our work that we implemented in a tool called Wuldo on synthesizing unrealizability logic proofs. So the remainder of the talk will be structured as follows. I'll explain to you what proofs look like in the logic. I will show you what our insight is that allows us to synthesize proofs in the logic, and then I'll give you an idea of what kinds of problems we can solve and to what extent we've been successful and where there's room for future work. So continuing with our running example, we'd like to prove that no term derivable in this grammar satisfies our example. Now typically if you want to prove something over an inductively defined set, which this grammar is, you need to do so by induction. And if you've ever done any kind of proofs in Hoare logic or proofs over loops, you know that when you have an inductive structure, sometimes it's not enough to prove things directly from the fact that you have, but you need a stronger fact, which is inductive, i.e. a loop invariant. Now, a similar situation occurs here. This fact by itself is not inductive over the structure of the grammar, but we can find a stronger fact that is inductive over the structure of the grammar. We'll call this fact a nonterminal summary, and in this case, the summary we'll use says that if x and y have the same parity, then the result of evaluating the expression has the same parity as x and thus as y. In other words, if x and y are even, then the result of the evaluation is even. And if x and y are odd, the result of the evaluation is odd. This ends up being something that is inductive over the structure of the grammar, and it implies the fact that we're trying to prove. You can compare these non-terminal summaries with function summaries and Hoare logic for recursive procedures if you're familiar with that. A lot of the ideas that we use here are inspired by that line of work. So how does a proof of this sort of a property proceed? Well, we want to proceed by induction over the structure of the grammar for E. We'll take this triple as our inductive hypothesis, and since we have 4 production rules, we have 4 cases. Now the first 2 cases are pretty routine. These are just singleton sets of programs, the singleton set X and the singleton set Y. So there's nothing interesting going on in these base cases because it essentially reduces to normal Hoare logic. The interesting cases are these 2 at the bottom, in which E appears recursively. Now, I won't get into too much detail about what exactly we do here, but the general idea is that we break the expression, for example, E and E, up into its subterms, and we do some magical application of our inductive hypothesis that allows us to derive the postcondition true to show that the inductive hypothesis holds on E and E. This talk is not so much about the logic, so I won't get too technical, but if people have questions at the end, I do have some auxiliary slides. Now, with a general idea of how these inductive proofs work in unrealizability logic, I want to communicate to you what our main insight was that allowed us to do synthesis of these kinds of proofs. So here I give you a proof written as a derivation tree. Don't worry, you don't have to understand too much of it. But the main insight is that we can separate a proof structure like this into 2 main components. The first component is going to be our proof skeleton on the bottom, and the second is our non-terminal summaries or our invariants on the top. So when we pull the invariants out of our proof, what we're left with is the structure over here that gives us which rules that we've applied and when we've applied them. So we sort of separate out the use of invariants from the strategy that we use to carry out the proof. And with this distinction in mind, I want to lay out the algorithm and then point you towards really the most critical and surprising part of it. Yeah, oh, sorry. So you can fill in the proof skeleton with a sort of second-order variable representing the non-terminal summaries. And what this does is this means that if somebody specifies a summary like above, you can plug it into the proof skeleton. So the idea is that given our grammar, we derive a single proof skeleton like this, which is actually strong enough to prove any true fact over the grammar. From the skeleton, we can extract verification conditions that are parametric in our unknown non-terminal summary O. And then these verification conditions let us check whether a summary will or will not be able to complete our proof. So if someone gives us a summary and says, I think this will work, we can plug it in and complete the proof by checking the verification conditions. And if not, we can try to synthesize a summary that satisfies the verification conditions to complete the proof. In either case, we end up with a non-terminal summary, which we can plug into the skeleton to finish things off. Now, the most interesting part of this whole algorithm is really the first step. And in principle, you would think there are an infinite number of ways that I can try to prove things, and there should be an infinite number of proof skeletons that I can use. So maybe I have to iterate through them or do some backtracking or some clever search to figure out what my proof strategy is going to be. But what's really interesting here is actually that you don't have to do that at all. You can fix a single proof strategy that's always guaranteed to work. To really drive this home, let's consider the search space of proofs. Here, the green dots are correct proofs, and a proof is sort of defined along two axes. The first axis is your proof skeleton, and the second is your summaries or your invariants. Now, in order to get a correct proof, you would think you would have to do something like this. First, I pick a proof skeleton, and then I pick a non-terminal summary, and I hope that I'm lucky and I've made good choices, and that when I plug the summary into the skeleton, I get a proof object that happens to be correct. Now, you can imagine that this is not the best way of doing search, because in general, you may have a good summary and a bad skeleton, or a good skeleton and a bad summary, so this can be kind of a challenging problem. But the insight that we had is that we can simplify this problem by taking our grammar, deriving a single proof skeleton with the following sort of magical property that if a proof exists anywhere in our search space, then a proof exists that adheres to this skeleton. So by choosing a single proof strategy, we can simplify what was a two-dimensional problem down to a one-dimensional problem. And then all that remains is to figure out what kinds of summaries are compatible with our proof skeleton. Determining the compatible summaries is relatively straightforward from here. We have a very formulaic way of extracting verification conditions from our skeleton. And then we can use these verification conditions to either confirm that an invariant is correct or to try to synthesize an invariant if none are provided. In either case, we end up with a complete proof. So that's the outline of how proof synthesis works in our framework. And I'd like to talk to you about our findings to give you an idea of what kinds of benchmarks we can solve and sort of how things look on that front. So I will tell you everything I'm going to say for the next 2 slides is under the paradigm where the user provides the summaries / invariants. So of course, we can prove our running example. Wouldn't be much of a talk if we couldn't. So for bit vector programs with finite sets of examples, we beat existing solvers. We can also prove sets of CLIA programs, or CLIA expressions, I should say, for sets of finite sets of examples. And here, actually, we're a little weaker than the domain-specific solver, but we don't feel too bad about that because Nagy is really optimized for exactly and only this sort of problem. And then somewhat more interestingly, we can also establish arbitrary Hoare triples over sets of programs. For example, here, we start with the precondition, x is divisible by 6, and our postcondition is x is not 1 mod 6. And this is not something that you can encode in a finite set of examples. So it's completely inexpressible in prior tools, but it's something you can prove using ours. And the most interesting class of examples is ones where we have this kind of functional specification, but we can't extract a finite set of counterexamples. So here I want to prove that none of the programs in this grammar are equivalent to x gets y. What is this grammar? This grammar basically contains programs which are nested if-then-elses, and the only assignments that you're allowed to do to x are assignments of constants to x. So if I wanted to construct a program that was similar to x gets y, I would do something like this. If y is 1, then x gets 1. If y is 2, then x gets 2. If y is 3, then x gets 3, and so on and so on and so on. And eventually I have to finish the program. Now, if I wanted to construct a finite collection of input-output examples that separates x gets y from this set, I could try to write down such a set of examples, but then I could always give you a program like this that hard-codes the values that I want over all of those examples. So in fact, in order to separate the semantics of x gets y from the set of semantics computable in S, I need to specify an infinite collection of examples. And with a slight extension of the things that I'm talking about, our tool solves these kinds of benchmarks as well, which I think is very cool and very exciting. So those are the positives of our findings. What are the negatives? So in many cases, our tool does require that users specify summaries. The reason for this is sort of twofold. First, sometimes the summaries require like very specific insight. That's kind of hard for synthesizers to find because the expressions get a little large. But second, and more importantly, a lot of the summaries require the use of existential quantifiers. So to drive that point home, a lot of our benchmarks based off the tool Nagy were using these sets of LIA expressions or CLIA expressions. And for these, you really end up needing an existential quantifier to describe the kinds, to describe possible coefficients, so that I can say that out is a linear combination of x, y, and 1. Now, the problem with this is, one, that Cygis solvers can't synthesize existentially quantified expressions, but two, that when I take this summary and I put it into my parametric verification conditions, suddenly I have a pi2 formula, a for all exists formula, where phi here is nonlinear because it involves this multiplication of coefficients. And this is something that SMT solvers hate. So these are a couple of like remaining obstacles, but I wanna wrap things up now and give you the summary and the take-home notes. So in conclusion, we presented an algorithm where, given an unrealizability triple, one can construct automatically a proof. The main insight that makes this somewhat tractable is that we can reduce our two-dimensional search space to a one-dimensional search space by fixing our proof strategy via a proof skeleton. And this can be useful for many applications, like reasoning about self-modifying code, pruning and program synthesis, proving program optimality, et cetera, et cetera. And also, I want to point out that our work presents some interesting use cases for niche solver features, such as Cygis solvers for existentially quantified formulas and over the theory of infinite arrays, and then also SMT for NLIA pi2 formulas. And that's the work of the talk, and have a really neat I would encourage you to check out. So that's all I have for you today. Thank you for coming, and I'm not taking any questions. That might have been this one. So I guess with first of all, great talk. I guess one of the main contributions is this ability to synthesize it.
We are in need of an
Testing.